the vascular stent, and yeah, how to evaluate the stress elongation strand modules. So before this part, any question? Any question? So no questions, like we go, go to see several movies first. And you guys, can you see me? Can you see my screen? So if any students can confirm with me, would be great. Or otherwise, you cannot see, please demand me.
Yeah, we can see it.
Great, thank you. So first one, it's about hot valve first. Yeah, the hot valve actually is I'm pretty interested in this kind of materials, and they are very soft, elastic, and multiple. For example, so every day, every minute, do a lot of ablation. They are contact with blood, and no blood clot, form, and always if close, it's we can say it's totally sealed, and the blood cannot go back. So here's several hot valve replacement option we can take a look at first.
My career started in the early 80s, and for the past 20 years, I have performed a lot of mitral and aortic valve surgery, and so tricuspid valve surgery, either repair or replacement, so that I would say that my clinical activity is focused for about 80% into valve surgery right now. The indication for heart valve surgery are obviously different from aortic valve and mitral valve. Aortic valve, the most frequent indication for aortic valve surgery is aortic stenosis. The valve becomes very calcified and doesn't open.
So this one's means So for aortic, we know have three part, right? And stenosis happens is blood clotting. This is one serious issue. So if you design materials, we always think about how to and control that by falling. This is anti-falling. We need anti-falling, and later blood compatible materials. Of course, the super elastic always requirement.
So there is no medical therapy for this condition, and we just have to replace this valve. For the mitral valve, the most frequent indication for mitral valve surgery is mitral regurgitation. The valve is leaking a lot. So for aortic valve surgery, we have to replace the valve when the valve is stenotic and narrow. If we have a mitral valve prolapse with mitral valve regurgitation or mitral valve leak, we can repair that valve with a high incidence of success, over 90%, if the surgery is performed by competent surgeons. There are some situations in which the valve is leaking, but a repair is not possible. Very often, this is in patients who had prior heart attack. There are two general types of valve prosthesis or artificial valves. One is a mechanical valve. Mechanical valve means that it's completely man-made. There is no biologic tissue in the valve. This is a mechanical valve. It's called a bi-leaflet valve. There are two little leaflets here, and they open and close. And then you see this cuff, which is a fabric called Dacron.
Yeah,
and this is the.
It don't look like some of the notes. The notes because the automatic translation somewhere. So that's the PET materials, the Dacron, as we already introduced in the lecture one. Is a polymer materials, and at around the suture kind of structure, and it's a textile structure, yeah, for fixing.
Where the stitches go in and anchor the valve where we want to position. And this can be an aortic valve or can be a mitral valve. The issue with this valve is when this valve is in the blood flow, the blood will tend to make little blood clots around all the hinge points of the valve. And
yes, that's the blood clot issue. So in our, I know, like, yeah, we have totally 4 projects. So 3 projects actually related to blood clot. Yeah, I never mentioned. One is stent. We definitely avoid. The brain, also, if we design a blood vessel in the brain 3D printing, so blood clotting is also significant issues. And how to avoid, otherwise we're called stroke and with the patient quickly die. Of course, the heart valve is another issues for in blood clot, and we should consider in our design.
For this reason, the patients who have a valve like this need to take a pretty a significant blood thinner called Coumadin or the alike. And Coumadin requires a very careful follow-up.
Any students can hear me when I stop the movie? You can hear my comments. Can you make a confirm to me? Yeah, perfect. Yeah, so that's I would like. Yeah, and so one several drugs like and one popular actually is the heparin. So heparin is like we can conjugate onto the stent or some materials blood vessel and the heart valve to control the blood the blood contact interaction with the device.
With the doctors and blood tests to make sure that the amount of Coumadin is the appropriate amount. The other type of valve that we have is called a biological.
So biological, yes, that's like we are asking you like for one group, that's like the stent and heart valve and the brain project all related to the biological tissue. Yeah, or tissue engineering way. They are biodegradable or like the tissue original from the scaffold you use from the other body, yeah, from all other animal. So that's the
valve or a tissue valve, and it's called in this way because a portion of the valve comes from an animal, and the animal can be either a pig or a cow. This is a typical example of a biological valve. And you see the internal part of the valve, you see that there is still a cuff of a fabric called dacron, but the inside portion comes directly from a pig valve. And this valve is a much more user-friendly in the sense that you need to take a blood thinner only for a certain period of time. And the downside of the valve is that it doesn't last as long as the mechanical valve. So the durability of the valve is very much related to the patient's age. If you are over age 70, this valve will last 15, 20 years. If you are younger than 60, it will probably last 10 years. And this is a cow valve here. And this doesn't come for a valve of a cow, but the tissue that they use is the sac that there is around the heart called pericardium. So this is called a pericardium.
So guys, remember pericardium is a kind of a membrane. It's a membrane. Its membrane is just to cover the heart tissue. So that's like kind of like epithelial tissue. You guys remember that one of my lecture in even the last lecture, we mentioned one material is a membrane cover on the bone. So that's the very similar tissue. So interesting, like this kind of tissue cover the heart, cover the bone. There are a lot of like kind of a regenerative capability there, and the collagen and the very richful resources of the useful a lot type several type of collagen and very nice even in the cell. This valve is non-cell, but the cells is also different type different from the other type of cell. They have a little bit stem cell capability. So that's very interesting. So that's like a membrane, yeah, covered on the heart tissue. So it's a pericardium. We use this one, do a lot of work.
Bovine pericardial valve. And for aortic valve, this has become the valve of choice, the bovine pericardial valve. We have obviously different sizes. So this is a valve sizer. So what we do, first we remove the diseased valve, and then we use this sizer to size the opening of the valve, and so we can choose the appropriate size valve. We have different size valve in the shelves, and the valve can be small, like in this one, or can be double size, depending on the size of the opening. The valve technology has improved significantly. And the valves have become more efficient. To give you an idea, you see how much bigger this valve is than this valve. Obviously, this valve is smaller, but the cuff around it in this valve is much smaller, and the opening in relation to the diameter of the valve is quite nice. So a lot of progress has made and then deployed right where the opening of the valve is. In theory, this is a much faster procedure. The other.
So you can speak about like, yeah. So definitely in the proper leaf corporation, we'll think about it. They are totally is like, yeah. Oh, yes. Yeah. No leakage happens on this way. And blood thinner, yeah, blood thinner, or like the some like heparin kind of materials, or yeah, the aspirin kind of things, yeah, should take or should be loaded onto the surface sometimes.
Improvement is that the overall procedure has become so standardized. You know, I have done 300 aortic valve replacement without losing a patient. So that it has become quite safe. The transcatheter devices are definitely one of the great achievements of cardiac valve technology. The valve is put at the tip of this catheter and then is passed through the artery in the leg backwards, up around the aorta and down where the opening.
So the procedure is very similar to kind of like the stent replacement, the procedures you see.
Of the valve is. The patient's valve is not removed. The patient's valve is left there. And the new valve is deployed inside the old valve. This has been used very much in patients who cannot have open heart surgery for some physical conditions that makes the surgery very risky. And the results are quite good. When a patient is being told by his cardiologist that he needs a valve replacement, the most important thing that the patient has to decide is where can I have this procedure done safely? And he should go to a center where a certain critical number of these procedures is performed every year. I think that there is.
So that's the hot valve. You see like several type generates like two type. One is like the or like a synthetic non-degradable. Secondly is bioresorbable, but the bioresorbable have two parts. You see, one is like direct from pig or cow's hot valve, and these decellularize, remove the cell, keep the mattress in the hot valve shape. And in the second part, this one is bioresorbable or biodegradable. So for the bioresorbable second part is like adjust the gate the biodegradable collagen materials and the 3D printing. Make a 3D printing. Or this one is like using a film, right? Cover the hot that film, make a matrix, and meanwhile to cut it into a valve shape. So some students choose the hot valve. It generates like if I got you emails to choose like aortic valve and the 3D printing. That's in the bioresorbable and the bioresorbable second part. Usually biomaterials is biocompatible biomaterials or biodegradable materials with elastic property and can be used for 3D printing. So that's the part. And now we move to the another one is the So this one is a stent, is a biodegradable stent. And you will see if you check the stent, and it's the 3D printing, you need to make this kind of mesh. And this mesh is already been like decided. That's no other structure can be expanded and shrink like this one. So that's already become a law. If you 3D printing, you definitely you need to make this kind of shape.
From its inception, the Synergy stent was designed for healing and to treat your most complex patients and lesions. The Synergy stent's unique coating is applied only to the abluminal or vessel side of the stent, allowing the luminal side to provide optimal healing.
This side we are coating some things like you can coating drugs, you can coating heparin for blood thinner, you can coat some cancer drug. This cancer drug is not a chemotherapy drug. It's not for cancer patients. This one, because we know some chemotherapy or cancer drugs, they are toxic to cells. So we use this way, localize the coating to inhibit the surrounding cell, like lipids kind of things, overgrowth. That's the way. And if like think about you put a smart property in some mesh part, you can put about printing some sensor inside. So that's a smart stent.
This coating consists of a bioabsorbable polymer that is 4 microns thick and is coupled with a market-leading everolimus drug, allowing for synchronous drug and polymer absorption. Coupled with the proven platinum chromium customized stent architecture, Synergy has one of the thinnest stent struts on the market at 74 microns.
So you see, like generates like the mesh, one mesh thickness is less than 100 micrometer, but 100 micrometer is acceptable.
Drug and polymer coating suppresses neointimal growth and may promote more rapid endothelialization and earlier healing, in comparison to conformally coated permanent polymer drug-eluting stents, which have been associated with delayed endothelialization and healing. In addition, the permanent polymer remains on the stent indefinitely and has been associated with late adverse events, including stent thrombosis. With the Synergy stent, shortly after the drug is released at 3 months, the polymer is fully absorbed, allowing the vessel to heal and providing patients with the freedom from long-term polymer exposure, eliminating a source of persistent inflammation and potentially reducing the risk of late stent thrombosis. The Synergy stent is designed for early healing and freedom from long-term polymer exposure. Heal with confidence.
So that's the one. Yeah. And this cell should be already done. And yeah, this one. Take a look at this one, how they biodegradable materials, resorbable biomaterial process.
Portfolio from the biomaterials portfolio is from ResBio, which is one of our biotechnology resource and development centers. ResBio's goal is to use advanced scientific and engineering processes to develop new biomaterials for biomedical applications. And this process is predicated on the notion that someone comes to them with a biomaterials need and they synthesize.
So take a look at this picture. That's what for all projects. Yeah, for all your team project, we can use the computer modeling. Yeah, for theoretical research, calculation. But also think about combination computational method and the products. So first one, which is the polymer library. Think about what the property we need and make a synthesize or 3D printing or what kind of functional property. Then finally, we test in the animal or in vitro and in vivo.
The candidate polymer from within their vast libraries and then characterize that polymer based on physical properties and computational processes. And through an iterative cycle, the end result is a new biomaterial that they can then test for further development. And one of the great examples of this has been the development of a new cardiovascular stent. So it has all the properties we've come to expect from stents, that it has some novel features, which are that it is biodegradable by a very controlled degradation process, and it's also radio-opaque, so we can image it and we can monitor.
So for examples, we put like a kind of titanium or like some iodine the chemicals. So for the X-ray, for X-ray check. So that's like we can put some like contrast chemical agents in the stent. Meanwhile, think about like for the stent, for a lot of materials in our research in a biorobot one, stent ones, or think about the flexibility. And for brain tissue, we think about the elastic modules should be very, very low, a few kPa, that'd be good. Yeah. But generally, we will not design a brain tissue more than 1 megapascal. That's of course bigger issue. And control the degradation rate is like depends on the stenosis situations. We customize design the materials with like different degradation rate.
Process as it proceeds when the stent is no longer needed.
In 2002, Viva Medical came to us with a brand new stent design, but they were also looking for a new polymer, a resorbable polymer, that could replace the commonly used metals. Metal stents have the disadvantage that they remain within the body of the patient for life and can cause long-term complications. Stents have completely changed the way we treat coronary vessel disease. Stents are an amazing breakthrough. Stents are tiny, but they have to be strong enough to withhold the forces generated by the flow of blood. They also have to deliver drugs into the vessel, and at the end, they have to safely resorb into the body of the patient. all of these requirements make the stents one of the most difficult medical devices to design. NIH grants allowed us to design polymer libraries using combinatorial methods that allowed us to home in on a set of promising polymers for the Riva stent in a process that took us months instead of years. Riva's drug-eluting stent.
So one like a combination with, for examples, yeah, we have a lot of reference how to provide the, for examples like elastic part. So have a different functional group. And another one in the blood degradation. And what kind of groups, chemical functional group, have yet for the degradation. And also think about hydrophilic, hydrophobic, because hydrophobic always lead to the degradation rate, and is getting slow and slow. So that's like multiple ways, just for examples, hydrophilic, hydrophobic property, and different functional group we have option, have a library. And the elastic part have a different design. And degradation part have a different design. So they make a combinational library. And late, we have a multiple, or like using computer or program, optimize and then narrow down for chemical synthesize. So they all right now using like machine learning, AI, put together to design new advanced smarter biomaterials.
Created hundreds of jobs, but more importantly, it will change the way in which we treat coronary vessel disease. The Riva stent is today in clinical trials, and we are very optimistic that it will lead to improved outcomes for our patients.
Yeah, the interesting things like recently, and FDA have some reported some issues in biodegradable materials. So how to design a good biodegradable materials, because we also need to think about the biodegradable products after they degrade. So what is a byproducts from this one will cause some issues, because some of byproducts after degradation, they cause some patient issues, and that's like leading to some products recall. And if you check there and Google something, the news you can get. But in Europe right now, pretty good and a market and clinical application. So that's for the stent part. And we also go to the MITs, like how to use a soft magnetic property and with beautiful structure design, and think about the mechanical property. And that's like we can change the shape. That's the super soft. And that's materials that's 3D printed. They can work and morphology shift. They can catch and make kind of mini robot capture like the hand function and make a kind of the so they're mechanical engineer. So the professor actually is also a mechanical professor. They also like using the kind of the SolidWorks for design, software for design, and make a module simulation for calculation to optimize the mechanical design for this device. Yeah, so that's several potential things like I want to explore to you guys and how they consider materials in their design in their project. I hope it will be good for your project. So now we move to the another examples for calculation examples. So it's about the a metal. Yeah, that's the example 2. Is a tooth plant or the metal plant. Yeah. So a stainless steel as an implant of diameter is 2 millimeter, length 20 millimeter, and this one is placed inside, which undergoes a tensor force of 100 Newton. Let's like estimate the change in length. And we also need to change if we design that using titanium for another material, so what kind of situation what happens if we put together, we think about. And in length, estimates the change range. And we have modulus is 200 gigapascal. So we know the diameter, diameter is 2 millimeter, and length is 20 millimeter, and we know the cross-section area. Yes, it's pi. Yeah, we just 3.14 millimeter square. Then we know the F is 100 Newton, and we can get the stress is F over A, 100 Newton for 3.14 millimeter square. So it's around this 1 Newton millimeter square. So that's megapascal, right? Then we go to the next part, and we calculate the strain as stress sigma, divided by elastic modulus. So what we can get is around 1.591 E, minus 4. And the delta L, we get to the strain. So the original range L times strain is around, this kind of, millimeter. So it's around 3.18 micrometer. However, if we choose the titanium, So yeah, in another case, if we choose like a titanium, for example, titanium implant, so what will happen? So we know titanium is 100 gigapascal. So we can get another one. Yeah, the strain is 3.114 E times this one. And meanwhile, we can get delta L. Delta L is L times strain, and we can get 0.68 millimeter. So that's around 6.4 micrometer. So the issues here's what like if we design two materials at the medical device, the first layer is SS, and the second layer is titanium for implantation, and we have a force 100 Newton. So we can get delta L prime, we have 3.18 around microns. Yeah, so if like in some location, and if more than, for example, more than 10 micrometer will cause some issues. So that's like during our designs, we should think about, the loading capacity and what is relatively, the strength changes. That's where cause some issues. And I will give several more examples like, so next one we have, let me give time. Take a look at it. Let me give one another examples. It's about it's a rubber drain tube. Okay, drain tube, and with the Poisson ratio, it's around 0.4, so pretty plastic. And the tube diameter is around 8 millimeters, and the range 25 millimeter. We have 100 Newton normal force applied outward and producing an extension of 0.02 millimeter. And we calculate one is normal stress. Second, normal strain. Third is Young's modulus. Number 4, decrease the diameter. Delta D. Decrease the diameter. So we know the Poisson ratio. Is 0.4, right? We have one direction elongation, the another direction is decrease, the shrink. So we just for this one. This one X. The other direction is Z. Okay. And we know the tube diameter 8 millimeter. Then we can get the area is around 52.56 millimeter square. And we know the force is 100 Newton. Then we can get the stress is 1.989812 Newton per millimeter square. We also can get the strain is delta L over L. Yeah, it's 0.8 micrometer. No, it's like 0.008, not no unit, okay, for the strain. And meanwhile, then we can get the elastic modulus. That's the stress over strain. So we can get this around 6. Yeah, this kind of way. Yeah, millimeter. And so we can get another ones like from Poisson ratio. We know, yeah, easy, yeah. This one we can get minus 0.02, and so what is delta D change? The diameter change, Z diameter change is like a decrease. We know the EZ time epsilon Z, the strain Z time diameter. So we can get the yeah, this one EZ. We know EZ times 5 equal to 0.116, and we can get delta D is like equal to minus 0.116. So here's like want to like show these examples is based on this one. The materials is original like this one. However, if we get elongation, the diameter will decrease. So slight elongation and a slight decrease in diameter. That's one will cause what possible reduction in flow. And another one's like think about like for examples like you will see like if the materials happens like this one for the filament, right? That's one could be titanium or stainless steel. So if I give a force, yeah, or the screw plate, the titanium or stainless screw or plate in bone implant or in the tooth. So with the force that's leading to what? Yeah, that's the original, this shape. We have a gap produced. A gap. So this gap, what will happen? A small gap. That's for what materials there? Yeah, bacteria can grow inside. Finally, cause some issues there. Yeah. So here's the today's lectures. Yeah. we got like some movies about like hot valve, stand, micro robot, all based on the soft tissue. And this soft tissue, which like could be used as 3D printing or like from totally non-degradable materials or degradable materials, and from the animal tissues. And meanwhile, we use a very basic mechanical. Take a look at like if two different for your bone, the stainless steel, titanium, or some other materials, even on the same force, but will cause some bigger other issues. Yeah. So in that, for example, in the tooth brand, tooth implant or some bone implant, some force, given like so we are from gap. The gap will leading to some bacterial grow inside, and that will lead into the implantation fail. Any questions? Any questions?
Yeah.
Yeah.
Can you go to the last example, and I didn't quite understand how do you calculate the last delta D? I didn't understand that.
Oh, delta D is like you see, we can from Poisson ratio, right? This one, we know the Poisson ratio is 0.4. We know this one is x epsilon x, so we can get the epsilon z.
Oh, okay, got it.
Yeah, z times this one. Yeah, because the diameter is 5, so we can get the change of the diameter of the tube.
So,
It's clear?
wait.
Yeah, perfect. Any further question? Yeah, if no questions, class is over. But like, I'm happy if you have some any questions to ask me and comments about your project, need my suggestions, please send me email. We have a meeting. Okay, thank you.